Okay, I am recording. And let me just ask all of you who are here right now, because again, I've had one or two students tell me they have difficulty getting into the meeting. Did anybody have trouble getting in from Canvas? Anybody have any difficulty doing that? Okay. So you just click on the join button and you get in, no problem, right? It doesn't matter how I start the meeting, because sometimes I'll start it from Canvas and sometimes I'll start it from WebEx, but I seem to wind up with the same interface, so it doesn't look different to me. Okay, I may need to get the IT folks involved with that one. Okay, so let us continue then with what we're doing. I'm going to start by sharing my screen with you, my browser, and basically we're going to look at our course. Okay, I'll leave the chat open in case you've got comments as we move along, but I'd encourage you, please, to just unmute yourself and ask if you have a question. It's a lot faster. And sometimes if the chat scrolls quickly, I may miss a comment or a question. All right, so here we are in our course. We're currently in week 4. So I'll get down there. Here we are. And you can see the only thing in this week was practice for exam 1. So this is like a catch-up week. If you want to use late passes to open up previous assignments, you can do that. But what I'm going to be using today is this practice for exam 1 file. If you were in class on Monday, I handed out a paper copy of that to you. So hopefully you still have that handy. If not, I would just encourage you, have some paper ready, because the idea is going to be to kind of actually work out the problems. It's not really been documented that students just watching an instructor work a problem actually learn how to do the problem. It's almost like you need that physical feedback of walking through the problem yourself, whether that's with a pencil, with a tablet, whatever you have, but to actually create the steps as you go. Okay, so I'd encourage you to take notes as we move along, only because it helps to reinforce that, body-brain pathway, and you're more likely to remember how to do the problems. The exam is similar, okay, but it's not identical to the problems that we're doing here. Here you have exam 1, okay, and again, you can see it's due on Sunday, the 19th. All of the assignments are due at 11:59 p.m. on Sunday, okay? So this exam, I opened it in class on Monday, and you saw you have an hour and 40 minutes to complete the exam, just as if we were sitting in a classroom. You can use any of the materials in the course. You can use Desmos, whatever calculators you're comfortable with, as well as the course material. The only thing you can't use is someone else's brain. Okay, so please, this is meant to be your work. Okay, I'd encourage you, like everything else, write down what you're working on. Okay, and then once you submit the exam, okay, see this exam 1 work file, assignment rather, this exam 1 work will let you upload a PDF or multiple photos. Okay, there are free online apps that'll let you take multiple photos and create a PDF, but you don't have to do that if you don't want to. I mean, in my mind, it's a lot easier to just upload one file, but that's up to you. Okay, and the point of doing this is so I can go back and regrade your exam, all right, and give you partial credit. Okay, and after that's done, when I'm done with that, I'll email you and I'll let you know that there's feedback. Okay, and it'll be attached to one of these 2 assignments. Probably the exam 1 work might be easier for me to attach feedback to. So please actually look at the feedback, because again, exams let me know how you're doing, but I also provide feedback to you so you can actually learn from the experience. The idea is to not just look at an exam, say, I don't like that score, and then trash it somewhere. It's to actually go back through it and understand where you might have had a misconception or where you might have made a process error. So that's how you get better at it. Okay, so again, I'm kind of hoping these are going to be more like 2-way conversations, okay, than just a one-way of where you do the work and I grade it. Okay, anybody have questions on the exam? Okay, I'm repeating all that because not everybody here was in class on Monday. Okay, so questions? Okay. Not seeing any. So I'm going to open this exam one practice file. Okay. And what I'm doing as we go along is I'm writing out how to solve the problems. Okay. If you open this file, it has the questions and then it just has an answer key, which to my mind isn't super helpful if I don't know how you got the answer. So what I'm doing is I'm actually working out each problem in detail. And again, I encourage you follow along. When I'm done, okay, in the week 4 live online sessions, I'm going to have the video that we're recording right now, as well as the complete practice exam with all of the solutions worked out. Okay, so right now in here, you've just got Monday's, from previous class video, as well as part of the practice. You're going to have the whole thing with today's video. Okay, anybody questions on where you can find the results of what we're doing? Okay, anybody questions on that? Okay, if not, and again, the chat's open if you want to type something in there. I'm going to open up that practice, so give me a moment to do that. It usually takes a minute. Okay, and then I need to share that with you. I'm going to share that content. Okay, so everybody should now see a page that has problems on it. And the first one is problem 17. Okay, is everybody seeing 17? Okay, everybody seeing 17?
Yes, ma'am.
Yeah.
Yeah, okay, great. Okay, now what I can do with these, right, this is more limit stuff, okay? And I'm going to try to work these problems in here where I can fit them. But I reserve the right for these more wordy problems to just open up another sheet and work it out so it's not crammed in, okay? I hate cramming in math because I always wind up losing negative signs and exponents and stuff like that. So where I can fit it, that's great. Okay, so here, remember the last time we met, we talked about finding limits graphically, like looking at a graph and determining, okay, as x approaches 2, what's the limit from the left? What's the limit from the right? What's the limit as we approach 2 period, right? And sometimes that was different from the function value at 2. All right, so here what we're doing is we're doing the same thing, but algebraically. And is there any reason why you can't just graph it and look at it? No, of course not. But you should be comfortable enough with algebra in a calculus class that you can get the same answer either way. Okay. And again, if you just use a graph and you use it incorrectly on an exam, I can't really give you much partial credit because you're not really showing work. If you say, hey, I looked at the graph and this is what it looked like to me. It's like, okay, but so let's do these algebraically, okay? So I have a symbolic rule for a function, right? So this is like saying the limit as x approaches -3 of f of x. And what's f of x? F of x is this rational function, okay? So if I want to do these algebraically, let me first kind of like put dividers in between these things. Okay, and then kind of try to do the work in between. The first thing's a rational function, and they want to know the limit as x approaches -3. Well, -3 squared is +9, plus 2 times -3, that's -6, minus another 3. So these two terms give me -9. The first term gives me +9. Just plugging in -3 isn't going to work because it's going to give me a 0 in the denominator. And remember, we said last time, putting zeros in the denominator gives you undefined stuff, right? Because you're essentially asking, how many times does 0 fit into something that's not 0? Okay, and basically you can't decide because 0 doesn't take up any space. It can fit 10 times, it can fit 100 times, it can fit 1,000,000 times. Okay, so dividing by 0 isn't okay. And you kind of know that. That's kind of a rule that you've ingrained. All right, but that's why it doesn't work. So what do you think the strategy is of simplifying this function? Okay, in 17, what should I try? Anybody have any thoughts? What should I try to simplify it? Just plugging in -3 isn't going to work. So what should I try? Okay, Miriam's suggesting factoring. Okay, can somebody else tell me what would that buy me? Okay, so factoring. Most people, they see a polynomial, that's what they do, they factor it. Okay, but what would that buy me? Why would I do that? Miriam, what were you thinking when you said factoring? What did you have in mind?
I mainly thought like as a way to like simplify it.
Okay, so what she's thinking is if I factor the polynomial on the top and the polynomial on the bottom, okay, maybe something will divide out, right? And I'll wind up with something simpler. And then maybe I can plug in the -3 and I won't get a 0 in the denominator. So it's kind of like taking a chance on this thing. Okay, so let's try that approach. Now, again, I told you there are factoring calculators on the internet. Okay, if you Google factor polynomial calculator, you will definitely get some hits. Okay, and you can put the polynomial in there and it'll factor it for you. Okay, that said, I know you can all factor. Okay, my numerator here is a difference of squares. Okay, and again, you factor that by taking the square root of each of the terms. So x is my first square root, 3 is my second, square root of 9 is 3. And then you put a plus and a minus. That's how you get the difference of squares. Okay, the denominator polynomials a little bit more difficult because again, you have to find two binomials. It's quadratic, so I'm going to factor it as a product of binomials. The first term's x squared, so I know I have an x as my first term. And then you look at this sign on the last term. It's negative. That means the signs in the binomials are mixed because that's the only way you'd get a negative last term, right? A positive times a negative. So you're looking for two numbers that multiply to give you -3, but when you add them, you get +2. That's the middle term. Okay, anybody got ideas? What should I plug in here? You can unmute. Say again.
3 and 1.
So which one's positive?
The 3.
The 3, right? And the 3 is positive because if you add a +3 and a -1, you're going to get the +2 in the middle. Okay. So I took Miriam's advice and I factored these, and you'll notice when you look at them, you have the same factor on the top and on the bottom. Okay, anybody remember from college algebra? What does the factor on the top and the bottom, what does that mean? Anybody remember? Okay, I'm not asking you, well, it means you can cancel them out. I know that. I guess I'm saying, what does the same factor on the top and bottom mean from the point of view of a rational function? What is this giving me? Normally, I wouldn't cancel it out, but I'm going to do that because I'm trying to take a limit. Okay. But what does the matching factor mean you've got? Anybody remember? Well, we know it's an undefined spot, right? Because any factor in the denominator of a rational function gives me an undefined output. Okay, so you can see here, -3 would cause a problem down here.
That make it a vertical asymptote or whatever it's called.
Okay, vertical asymptotes are factors that are just in the denominator. Okay, when you've got a matching factor like this, you have a hole in the function. Okay, you have a hole in the function with a matching factor like this. Okay, remember when we talked about holes in continuity, we said they were removable? They were removable discontinuities. Part of the reason we can do that is because it'll factor out. Okay, now the hole is still there in the rational function, but remember, from a point of view of a limit, holes really don't matter because, again, the limit as you approach the hole from the left is the same as the limit as you approach the hole from the right. So the limit exists as you approach that hole value. That's not a problem. Okay, vertical asymptotes are a different story. The factor that's left behind in the denominator, this x minus 1, okay, if you set that equal to 0, you would get a vertical asymptote at x equals 1. And that's not a discontinuity you can remove. So the function is still undefined there. The good news is we don't care about that because we're interested in the limit as x approaches -3. That's where the hole is. And we know that limit exists because of the way holes behave with limits. Okay, is that description clear? Is that clear? Anybody questions so far? Okay, limits exist as you approach an x value where there's a hole. So this is an okay thing to do. Then what you can do is you can rewrite the limit of what's left behind. Okay, and you can see, oh, hey, that's all right. I can plug in that value -3 now and nothing bad happens. Okay, so -3 minus 3, I'm plugging in -3 for x. That's -6 over -4, and that's 3/2. Okay, so the limit as you approach x equals -3 of this polynomial, this rational function rather, is 3/2. That means as I get closer and closer to x equals -3, my output value is getting closer and closer to 3/2. Okay. Now my idea is a picture's worth 1,000 words. So that's the algebra. Okay, factor the polynomial on the top, factor the polynomial on the bottom, see what you can factor out, then see if you can plug in the value of x at the limit, the limit you want to take. But let's take a look at what this means graphically. All right, so I'm going to go to Desmos. Okay, and I'm going to put in that function. Plus 2x. All right, so here's my function. Okay, you can see, all right, there's definitely a vertical asymptote, and where is it? Well, it's at x equals 1. As a matter of fact, Desmos will let me actually graph that. And you can see the vertical asymptote there. Okay? Now, we said at -3, the function's undefined. Well, where's -3? Right here. I have to kind of hit it right on the nose. See the undefined spot? But what we're interested in is the limit on either side. Okay, if I go slightly to the right of my hole, you can see it's about 1.5. It's a little big because the function's going up. If I go to the left of the hole, it's a little bit less, but it's close to 1.5. Okay, so what you want to notice is your output value is close to 1.5. Whoops, I'm in the wrong spot. Sorry, meant to put that in the chat. Output Y value is close to 1.5 on either side of the whole at x equals -3. Okay, again, I'm trying to make sure everybody gets this concept of a limit. Right at -3, there's a hole, so it's undefined. Okay, go slightly to the right, slightly bigger than 1.5, slightly to the left, slightly smaller than 1.5. But remember, 1.5 equals 3/2. Okay, and that's the value we got when we solved for the limit algebraically. Okay, everybody cool with this? Anybody questions? All right, so the picture should give you the same answer as the algebra. If you want to do the picture first, go for it. Then you know what the answer should be algebraically, right? The idea is I'm trying to get you comfortable enough with all the different representations that you can do with calculus that you never walk away from a calculus problem saying, well, I don't know if I got that one right. You're going to know, okay, because you've got multiple ways to check. Okay, so use the multiple ways to check. All righty. Questions on this one? Okay, come back to the notes. All righty, so basically, here's one strategy with a rational function. Okay, strategy with a rational function is factor it. Okay, factor it and see what you can divide out. Okay, so that's a rational function strategy. What do you think about number 18? Okay, how would you do 18? How would you do 18? Anybody thoughts? Well, what kind of a function
Well,
is this?
it's going to be undefined because there's going to be a 0 in the
Right,
denominator.
right. See, you can see the problem. If I plug in 0 the way it is, I get a 0 in the denominator, just like I did with 17, right? When I plugged in -3, my denominator became 0. So I had to massage the function a little, this algebraic expression, in order to make it work. Okay, so what sort of thing is this? Okay, let's assume this is f of h, since h is my independent variable. Okay, what sort of function is this?
Rational.
Yeah, it's a rational function. So what's a good strategy for a rational function? What do we do up here?
Factor.
Yeah. Okay, so we're going to try to factor. Now, don't let the fact that you've got h minus 1 cubed scare you. Okay? Yes, there are shortcuts for figuring out what the coefficients should be. Okay, if anybody's ever heard of binomial coefficients, they give you a pattern for foiling out something like this. Okay, but you can do it yourself. Okay, h minus 1 cubed is h minus 1 times h minus 1 times h minus 1. Okay, and yes, there's a factoring calculator that'll, this is the factored version of this, but I want to know what all the terms are. So you can do them 2 at a time. Okay, so you're just foiling h squared minus 2h plus 1. That's the first 2 terms multiplied, right? And then multiply by another h minus 1. Okay, and you're going to distribute both of these terms across all of the 3 that you've got already. So everybody understands what I did? I multiplied the 2 h minus 1s and I got this. And again, you can use the pattern I showed you. Square the first term, h squared. Square the last term, positive 1. Okay, multiply the 2 terms together, negative 1h. Double that, negative 2h. There's your middle term. Okay, and now the other ones just distribute. Distribute and combine like terms. So I'll do the h first. And then the minus 1. Okay, and notice distributing the minus 1 means I have all the terms in the first trinomial except the signs are all reversed. Okay, and then it's just a matter of combining your like terms. Okay, so I have squared terms that I can combine here and here. And then I have h terms I can combine. Okay, so this is going to give me, if I actually combine my terms, okay, h cubed. Okay, then I have a minus 2h minus another, a minus 2h squared minus another h squared, so minus 3h squared. Okay, then I have plus 3h minus 1. Okay, so what I wrote here for number 18 is the complete expansion of h minus 1, the whole thing cubed. Okay, and I'm showing you how to do it step by step if you're not comfortable with binomial coefficients, okay, to just expand it. Okay, now that's this part. Okay, but you can see we still have this plus 1 hanging out over there. Okay, so I have to put that plus 1 there. Okay, everybody see what I'm doing? Okay, do you see anything else you can simplify in that numerator? I just wrote the denominator again. See anything else? Okay, take a look at the numerator.
Yeah, 1.
Yeah, basically, you see the minus 1 plus 1 at the end, right? They cancel out, and then look at what you got left. Now, what do you notice?
You can take out the h.
Take out an h, okay? So now I have the limit as h approaches 0, factor out an h. That gives me h squared. And again, I've run out of room, so let me try this again. Okay. So that's h squared minus 3h plus 3 over h. So I've divided out an h, right? So that dropped my exponents by 1. And most importantly, look what it gave me over here. It gave me that 3. Now I'm going to cancel out the h's, and I have the limit as h approaches 0 of h squared minus 3h plus 3. Okay, everybody see that? Once these h's are gone, I don't have a denominator anymore. I just have this up here. Okay, can I plug in 0 for h now? What do you think? What happens if you plug in 0 here? 0 squared is 0, minus 3 times 0 is 0, plus 3. Anything undefined happen? What do you think, guys? Okay, so
But
here's
is it,
what
it's,
0
it's not
squared.
defined, right?
Why is it not defined? What is undefined about this expression? The denominator went away.
That's a great question.
Anybody have an answer? A hypothetical answer? Everybody see why we got rid of the H on top and the H on the bottom, right? It came with an H in the denominator, and that's what was screwing things up. We couldn't plug in a 0 down there. But we massaged the numerator enough, we were able to factor an H out of it. And then we had an H on top and an H on the bottom, and I crossed them out. That leaves H squared minus 3H plus 3 over 1. Okay, which is like saying no denominator. There's no problem with plugging in H equals 0 here. Okay, this is 0 minus 0 plus 3. So your limit is 3. Okay. Anybody have a problem with the algebra here? Okay, I can tell you don't like this problem. You really don't like this problem. Okay, so please ask some questions. Ask some
Algebra in
questions.
there.
No, yes, maybe. I need to get rid of these red lines here because they're confusing. We'll do all the other problems on sheets so they're not jammed in. Okay. So essentially the key here was when this minus 1 plus 1 canceled out, every term in the numerator was left with an H in it. And then I was able to factor out an H from every term in the numerator, and that let me divide out an H in the numerator and an H in the denominator. And that just left me with H squared minus 3H plus 3. When I take that limit, all I have to do is plug in a 0 for each of the H's. There's no denominator anymore, so nothing's undefined. It's just 0 minus 0 plus 3, and that's 3. Okay, so the trick here was using factoring to get rid of the denominator. Okay, here we didn't get rid of the whole denominator, we got rid of the problematic part of it. Here we got rid of the whole thing. Yes, no, maybe? Questions, people? Okay. Let me ask you a question. If you had a problem like this on the exam, could you do it? Algebraically. Could you do this one?
Yeah, it would just take me a while.
Okay. Would you do this one? What's sticky about it, aside from foiling out the cube? What was hard to understand about it?
I don't think it was necessarily hard. I think it's just making sure you follow all the right steps and
Right.
all
Okay,
the
so
other stuff.
basically what this stuff is trying to show you is you need to be able to find your way through the woods. Okay, it's not just a matter of, oh, these are all problems of one kind. So I just do like 30 problems all of one kind, and then I say I know how to do that. What you need to be able to do is to look at a problem you've never seen before and decide what sort of mathematical technique will work here. Okay, and that's what I'm trying to explain to you as we go along, because that will help you develop your mathematical thinking. That's what's going to be really useful out in the world, okay? Because, like I said, nobody's got an answer key. You've got a problem, and you've got to decide with a bunch of other people, how do I approach this? Okay, and if you can get it into a state where you can use a calculator or leverage some sort of computational device to get the answer, that's great. But you've got to get it there first. Okay. All right. So enough of that. That's number 18. I'm going to do number 19 on a separate sheet because I'm getting way too crowded. My writing's too large. Okay, but let's take a look at number 19. Okay, before we write it over on a separate sheet of paper. Okay, and let me just ask you, how might you do 19? How might you do 19? Anybody have any ideas? Can I just plug in 0? Would that work? You can't plug in 0, right, Raven? You can't plug it in because you'd have a 0 in the denominator again. Okay, and again, you're not allowed to divide by 0. It's undefined. So what sort of algebraic manipulation can you do on 19? Okay, what kind of, you got to break the square root down. Yeah, or even better, how about we get rid of it? Maybe get rid of it. Okay. So the problem here is this is too simple in the denominator to do anything with. So what Raven's suggesting is do something with the square root, and maybe we'll get lucky again and be able to factor out an x. Okay. Now, one thing I know they probably taught you a long time ago, maybe in intermediate algebra, was the idea of rationalizing a denominator, or the concept of rational. Let me see if I can spell it. Rationalize a denominator or a numerator. Okay. So basically, I know most people in intermediate algebra probably never rationalized a numerator, but it works on a numerator as well. Okay, if you want to get rid of the square root. Okay, I know in lots of classes, they tell you, oh, if you see a square root in the denominator of a fraction, you rationalize it to make it go away. But nobody ever told you why would you do that. Okay, and there's no reason to do it anymore. As a matter of fact, there are lots of examples in physics where you probably want to leave the square root there because it's more telling of what you're actually working with. But back in the day, and now I'm talking, oh, I don't know, about 40 years ago, there were no calculators. You couldn't type in square root of something and get an approximate answer. You had to use a device called a slide rule. Okay, I'll type it in the chat. Slide rule. Okay, and if you're ever really bored, get on the internet, type in slide rule, see what it shows you. It's a mechanical device that was invented back in the 18th century, pretty much. Okay, and you would use it to do calculations. Okay, it was real hard to do square roots on a slide rule. So that's why if you had them in your denominator, you tried to get rid of them. So it was an artifact of the computation devices that were used at the time. Okay, nowadays, there's no real reason for doing it. But in this case, we might want to rationalize our numerator to see if we can factor out an x. Okay, so I'm going to copy this problem over, okay, on a separate sheet. Okay, and we'll see if we can rationalize the numerator. Okay, so here's number 19, and it's the limit as x approaches 0, 1 minus the square root of 1 minus x squared over x. Okay, so the way you rationalize a numerator or denominator is you want to multiply by the conjugate. Okay, this is a mathy word. And all it means is take the same two terms that have the square root and just switch the sign in the middle between the two terms. Okay, so here's what I'm going to multiply by. Okay, this might look to you a lot like the pattern for a difference of two squares, right? One minus the term, one plus the term. You multiply them together, you get a difference of squares. That's the idea. If I square a square root, it goes away. And that's what I want to happen. But since this is a fraction, okay, I'm not allowed to just multiply the numerator. I need to multiply the denominator by the same thing. Okay, so this is just a fancy form of 1, right? Because the numerator and denominator match. It's a fancy form of 1. Okay, everybody okay so far? Everybody okay with this? Okay, again, I'm assuming even if you weren't able to pull this from the reaches of your mind, you were able to recognize it. Like, yeah, I remember seeing this. I'm never sure what good it was, but I guess I'm seeing it now. Okay, so I'm going to rewrite my limit statement so I don't lose it. Okay, and then I'm going to actually multiply my two things in the numerator together. Remember, this is just like FOIL. Multiply the first terms, multiply the outside terms, multiply the inside terms, and then multiply the last terms. Okay, so again, I can do a FOIL up here. But remember, I told you it's quicker when you're multiplying two binomials, and these are a pair of binomials, to just do it rapidly, okay? So I'm going to square my first term. Well, my first term in both cases, okay, is a 1. So that's 1 squared is 1. Okay, since this is difference of two squares, I'm going to take my last term and square it. The last term is 1 minus x squared, square it. Okay, and since this is plus and that's minus, I get a difference of squares here. Okay, if you're lost at this point, your problem isn't calculus, your problem is algebra. Okay, please reach out to me and I can give you some resources to help you remember how all this works. But all I'm doing is foiling this. Okay, only I'm foiling it quickly because I remember the pattern for difference of squares. Square the first term, square the last term, put a minus sign between. There's no middle term here because of the minus plus. The middle term will cancel out. It's only when you've got the same signs here, when you're actually squaring a binomial, okay, that you wind up with a middle term. Okay, so if these were both minuses or both pluses, they'd have a third term down here. Okay. Then I'm going to multiply across the denominators, and that's just going to be x times 1 plus the square root of 1 minus x squared. Okay, everybody okay with the algebra? Anybody stuck? Okay, let's do some simplifying then. Limit as x approaches 0. Okay, 1 squared is just 1. What happens when I square this square root up here in the numerator?
Or yeah, the square root goes away, right? It's
The
just be
square root goes away,
squared.
and I'm left with 1 minus x squared. Okay, so squaring a square root, that's an inverse operation. It undoes the whole square root. Okay, this is still okay. Next thing is, well, let's take care of this minus sign. This is the limit as x approaches 0 of 1 minus, now the minus sign distributes to both terms in the numerator. So that second one has a minus sign in front of it. And the x squared now is a plus. Okay, so that's I got rid of the parentheses. Okay, everybody all right with it? I'm just distributing this minus sign to both terms that come after. Okay, what do you see in the numerator? Do you see in the numerator? Anything simplified? How about this? What about 1 minus 1? Does that cancel out? I got positive 1 minus a 1, so they cancel out, and I'm left with this. Okay, now what do you notice? The x, yes, Richard, the x in the numerator. Okay, remember, x squared is just x times x, right? So what happens here? One of the x's goes away. Okay, and I just got rid of my problem in the denominator, which was a 0 down there. Okay, so here's what I have now. I have the limit as x approaches 0 of x over 1 plus the square root of 1 minus x squared. Okay, because I got rid of that multiply by 0, right? Now all I have to do is plug in 0 for x. Okay, now let's take a look. This is the square root of 1 minus 0. Well, that's 1. Square root of 1 is 1. So I have 0 over 2, and that's 0. After all that work, the limit's 0. Okay, but what was important was not the 0 in the numerator. That's okay, right? That's perfectly valid. I needed a non-zero number down here in order for this to be defined. 0 over 2 makes sense. It says, how many 2's fit in 0? That's easy. None of them. Okay. Another way to view it is I have 0 cookies and I want to share it with 2 friends. How many cookies does everybody get? 0. Okay, that's not the same as dividing by 0. Okay, this is a valid number. Okay, because I know a lot of students look at, go ahead.
How'd you get the 2 again? Just
okay.
Bottom half in the denominator?
Right, this is 1 minus 0 square root of, so that's the square root of 1, and the square root of 1 is 1. So now I have 1 plus 1.
Oh, okay.
Okay. And again, this is something, this square root here is something you can just type in on a calculator. Okay. The algebra, not so much. Okay. This is kind of the level of algebra you're going to need to do in a calculus class. And more often than not, it's ahead of actually doing any calculus. Okay. It's all right. I know a lot of calculus teachers make students really simplify answers. That's only important if you're going to use it to evaluate something. Why is that? Well, a big, complicated, messy answer is error prone if you start plugging values in. But you can see with these limit statements, it's important to be able to simplify things in advance of actually doing any calculus. Here's the actual calculus step right here in this last line. Okay, actually taking the limit. The rest of it is algebra, algebra, algebra. Okay. And like I said in class on Monday, the point of algebra is to simplify things. Okay, questions on this one? Right. I want to make sure we have plenty of time to get through everything here. Okay, not seeing questions. So I'm going to go back to my notes back this way. All right. So we did number 19. Okay, so let's take a look at number 20. Okay, we have a same type of limit. Okay, how would I do 20? You're really working your algebra muscles today. How would I do 20? Can I just plug in t equals 0?
Yes.
Okay, so that would give me 1 over 0 minus 1 over 0 plus 0. Is that okay? What do you think? Okay, Andres is saying no. Raven's saying no. Okay, do you see the zeros in the denominator here? Okay, so I can't do this. Okay, it's undefined. Right, whenever you've got a 0 in a denominator. So, okay, we know we have to do some algebra here. Okay, how would you algebraically manipulate this one? How would you do algebra on 20? Anybody ideas? More factoring. Okay, there's some factoring you can do in the denominator, but these are fractions. Being subtracted, right? These are two fractions being subtracted. Factoring's a possibility for part of it, but what could you do with them? Anybody have any thoughts? This is like saying 1/2 minus 1/3.
Common denominator.
Yeah, you can actually do the subtraction. Do the subtraction. That might simplify things. Okay. So let me see if I have any room on my separate paper to put 20. I can probably get it started down here. And it's the limit as t approaches 0 of 1 over t minus 1 over t squared plus t. Now I'm going to start by taking Andre's advice, because what I need to do in order to find a common denominator, right, to add the algebraic fractions, is I need to see what makes up both of them. Right, so let's start by factoring.
You got a graph paper, or are you still on the questions?
Yeah, I'm in graph paper. Can you see it?
No, I don't think it's sharing. I still see
Okay.
the questions.
All right. My bad. How about now? Can you see it now?
No, it's still the
All right, hang on.
no, you're good. I can probably figure it out. It's probably me.
No, can anybody see the graph paper?
What? What? All right, yeah, it's probably just me then.
Yeah, I can see it.
Okay, cool. Let me
I'm-
know if the technology horks up. I gotta fix it.
Yeah, no,
Okay.
I'll just leave and come back.
Oh, I'm sorry.
No, you're good.
Okay, we won't go too far, don't worry. All right, so the first thing I'm gonna do is what Andre suggested, and I'm gonna factor my denominators. Okay, t doesn't factor, it's too simple. But if you look at the other denominator, you'll notice there's a t in both of those terms. So I can divide out a t, and that second denominator I'll factor like that, right? You can check by multiplying it back. T times t is t squared. T times 1 is t. Okay? Now what I can tell is this denominator t fits inside the other denominator. See the factor t there? Okay, so my least common denominator is actually this denominator. Okay, that's the denominator I want to use for both. Okay, now again, if I want this denominator to be t times t plus 1, I need to multiply the denominator on the left by t plus 1, right? But I also have to multiply the numerator by t plus 1 because that's a fraction. Okay, so let me rewrite my limit statement. I'm going to leave my second fraction alone because that's got the right denominator. Okay, and here's what I'm doing with the first fraction. I'm going to multiply the numerator and the denominator by t plus 1. Everybody remember that strategy for finding a common denominator? Okay, basically you look at the least common denominator and then you look at the other denominators and you multiply them by something that'll give you that denominator. You multiply the numerator by the same thing. Okay? Anybody questions on that part? So here's what this is now. I have t plus 1 on the top minus 1. Okay, remember how you subtract fractions. You subtract the quantities in the numerator like that, and you write them over your common denominator. Okay, so you subtract your quantities in the numerator and you write them over the common denominator. Okay. Now you can notice the same pattern again. I've got a plus 1 and a minus 1. Those cancel. And now my fraction is the limit as t approaches 0 of t over t times t plus 1. Okay, the ones, the plus 1 and the minus 1 cancel out upstairs and just leave a t. Can everybody see what to do next? What should I do next?
Up the t's.
Yeah, cancel out the t. Now, when you're dividing out, you're saying t goes into t once, t goes into t once. So this becomes the limit as t approaches 0 of 1 over t plus 1. Can I plug a 0 in now?
Yeah.
Yep. This gives me 1 over 0 plus 1, which is 1 over 1, or just 1. Okay, so that was kind of like a crash review of algebraic manipulation from intermediate algebra. Okay, and again, I really wish people had been honest to students back then and told them you're going to need this when you get to a calculus class, even if it doesn't seem terribly useful right now. Okay, because a lot of it is skill and drill back there, but now you're actually going to use it to simplify things. Okay. All right, questions so far? Questions, guys? All right. Now, before we get to 21 and 22, okay, I want to share a simpler problem because this is an exponential function. This is technically a logistic function. And students are generally not as familiar with these as they are with, well, rationals or polynomials. But what do you notice about the limits here in 21 and 22? What do you notice about the limits? Anybody notice anything?
They're going to infinity.
Yeah, infinity and negative infinity. Now, there's a specific strategy for handling limits at infinity, okay? Not so much with these, okay? There's just like a rule of thumb for exponential functions, and we'll see it in my next example. So I'm going to go past all of this, and I'll show you this example. This is another example I just came up with. It's not on your sheet, okay? But I wanted to share it with you anyway, okay? And you can see I managed to clip a little Desmos graph of this function, okay, on the sheet so you can see how it works, okay? So the strategy when you have a limit as x approaches infinity, okay, of x squared minus 2x minus 3 over x squared minus 9. There's a strategy, okay? And here's the strategy for rational functions. Divide all terms by the largest power of x. Okay? Now, if I look at this expression here, largest power of x is what?
X squared.
X squared. Okay? So I have x squared divided by x squared minus 2x divided by x squared minus 3 divided by x squared. X squared divided by x squared minus 9 divided by x squared. Okay? This is perfectly okay algebraically because I'm doing it to everything. Okay, I'm dividing by x squared. Okay, the next step is to factor out the common factors. Okay, now you look at this over here. I'll just write the limit statement again so we don't lose it. What's x squared divided by x squared, folks?
One or X?
1. Yeah, it doesn't matter what x is. Okay, when you've got a numerator and denominator that match, you've got a 1. Okay, then I'm going to divide out 1 power of x. Okay, so I have an x to the first in the numerator, x to the second in the denominator. If I cancel out one of those, I'll have 1x in the denominator. Okay, and then this is 3 over x squared. Nothing simplifies there. All right, let's look at the denominator now. I have another x squared over x squared, right? That's a 1. And then 9 over x squared, that doesn't simplify. I can't cancel out a power of x. Everybody understand what I did here? I have 1x in the numerator, 2 of them in the denominator, x times x. So I just got rid of 1. Okay. Now, here's the trick that we're going to use with exponential functions. These are functions, these are fractions, okay, that have a denominator that's going to blow up. Okay, everybody see these fractions in my large expression? 2 over x. Okay, 3 over x squared, 9 over x squared. And I'm going to let x get huge. That's what approaches infinity means. Okay, so let's take a look at some example fractions. Okay, suppose I have 1 over 1. Okay, that's a 1. 1 over 10. That's 0.1, 1/10. 1 over 100. That's 0.01. 1 over 1,000. 0.001. Okay, what's happening as these get large? What's happening to the value of your fraction? Okay, so as your denominator is getting bigger, what is happening to the value of the fraction?
Smaller.
It's doing what?
It gets smaller.
Yeah, value is getting smaller. Okay, so if you have something like this, one over a billion, okay, you're going to wind up with okay, what is this number close to? Point 0.00000. What is that close to? It's a really small number. What is it close to, folks? Not a trick question.
0.1.
Yeah, 0, close to 0. Yes? This number is 1/1 billionth. Super tiny. So as my denominator gets huge, that is, approaches infinity, the fraction approaches 0. Okay, usually the way this is written in a calculus book, it's written like this. The limit, sorry. The limit as x approaches infinity of 1 over x equals 0. Okay, the limit as x approaches infinity of 1 over x to any number approaches 0. Okay, because it just gets there faster, right? If I square a really huge number, I'm going to get to 0 faster. And again, I'm approaching it. I'll never equal it, but I'm going to get as close to it as you want me to. You want 100 zeros after the decimal point? I can get there. Okay? So this is the fact you're going to use here. Okay? All of these fractions will approach 0 as x gets huge. Okay? So basically, you're going to get a limit that looks like this once you take it. Okay, and that's just 1 over 1, which is 1. So this limit is 1. Okay, so you divide out the largest power of x, and then any fraction with an x in the denominator is going to become 0 as x approaches positive or negative infinity. So you can ignore it. See, it turned into 0 here. Anybody questions about that algebraically? Okay, good with the algebra? Good with the algebra. Okay. All right, now let's talk about it in terms of your rational function. Okay, essentially what you're saying is, or what you're asking is, what happens to this function as x gets really negative okay, or really positive. Okay, and again, what you're seeing here is your horizontal asymptote. Whoops. Okay, and again, as this graph goes all the way out this way, it gets closer and closer to y equals 1. And as it goes out this way, it's going to get closer and closer to y equals 1. So finding a limit at infinity is really finding the horizontal asymptote of a rational function. Okay? And you might remember from college algebra, if the degrees in the rational function are the same, okay, the horizontal asymptote is the ratio of your leading coefficients. There's 1 over 1, which is 1. Okay, it's the end behavior of your function as x gets really large or really negative. Okay, so again, see the connection? See the connection to the horizontal asymptote on the graph? Okay, this is what the graph gets close to as you go way out here to the right or way out here to the left. That's the y value you're getting close to. Same thing as the limit. Asymptotes and limits are similar. Okay, you get as close as you want. Okay, let's go back over here to the notes. Okay, so that's one with a rational function. These are exponential functions. Okay, and what you need to figure out with the exponential functions is just what's the sign on the exponent. Okay, so basically, as you approach negative infinity with this, you're going to wind up with a negative exponent. Okay. Okay, so basically negative exponents, as you get larger and larger, the whole limit is going to approach 0. Okay, and again, you can see this if you graph it in Desmos. All right, so again, here I'm headed towards negative infinity. Negative infinity in my exponent is going to give me a fraction. Okay, so what I'm going to say here is the limit is going to be 0. Okay, and I'll show it to you graphically. All right, let's look at this one. Okay, this is y equals e to the 5x. Okay, now again, you can see as I go towards the right, my y values increase without bound and very rapidly. But look at what happens if I go towards negative infinity. All right, Desmos is even telling you the value is 0. It's not. But Desmos is only carrying 2 decimal places. And you can see that by the time you get out here, here's, 0.2, 0.1. By the time you get to -2, your y values are less than 1/1000. But again, they're not 0. So you can see as you go out towards the left, your y values are approaching 0. So again, if you're not comfortable with exponential function limits, just graph the thing and take a look at what the y values are as you move towards that x. Okay, so see it, the graph. Everybody see it on the graph, what I'm trying to show you? Okay,
Yeah.
exponential functions, logistic functions, they're easy to do graphically. Okay, and if you remember on a rational function that the limit as you approach, as you approach infinity in either direction is your horizontal asymptote, you've got that nailed too. You don't need to do the algebra. Okay, because they're the same thing. Okie doke. Let's see what else we have. I'm trying to move this a little faster. Okay, now take a look at this number 22. Okay, remember what I said, negative exponent, the limit approaches 0. Okay, but see over here, okay, here I'm approaching, t is getting larger and larger, but see the negative 0.08 in front? That means this is going to have a negative exponent. So the term is going to approach 0. Just the term I have circled, right? Because this is going to be e to a very, very negative number as t blows up. Okay, so you're going to be left with 28 over 2. Okay, and that's just 14. You can graph this function and you can see what happens as t gets really huge. And I'll do that for you just to show you. But again, the trick here is e or some base raised to a negative huge power approaches 0. Okay, because why is that? Negative exponents are like fractions. Okay, 1 over a big number. And I just showed you 1 over a big number approaches 0. Okay. Let me show you this one on Desmos just so you're comfortable with it. All right, so this one is y equals, and that is 28 divided by 2 plus e to the negative . I'm going to use x because x is what we're using here. All right. All right. So now we want to let x get really, really large. I'm going to zoom out. Okay. Here's the graph of the function. And you can see by the time I'm out here, look at my y value. Everybody see the y value? Okay. Okay, so the limit is the y value you're getting close to as x gets huge. Okay, and remember, Desmos is telling me 14, but it's really probably slightly less than 14. Okay, when I'm over here, you can see 13.9999, and Desmos runs out of decimal places by the time I get around 110. Okay, my x value, and then it stays pegged. But just realize it is still slightly below 14 and it won't equal it because it's an asymptote. Okay, see this one. See this one? Anybody questions? All right. So my advice to you is try to remember a few rules of thumb. If you have an exponential function raised to a negative power, that's like 1 over the base to a positive power. So you've got a fraction with a big denominator. Fractions with big denominators are really small numbers. So they approach 0. Okay, so that's how you handle limits at infinity. Okay, so again, questions on limits at infinity. Okay, guys, please make sure you understand these, okay? And ask me separately if you're not comfortable asking now. Okay. Gonna switch back. Oh, good. That's great to hear it. Okay, let's take a look at the questions we have left. It's kind of like 23 through 28, and I'm hoping to get all of those done in the next 20 minutes. Okay, I especially want to do 24, 25, and 26. Okay, The rest of them, I think you can manage to work through just by looking at my notes, okay? Let's take a look at this. True or false? If the domain of f is all real numbers and the limit as x approaches 2 of f of x is 6, then the function value at 2 must be 6. What do you think about 23? Is 23 true?
True. I think it's true. I'm probably wrong though.
Okay, now the trick is, if you think it's false, find a counter example. That means you want to basically see if you can come up with a function that's defined everywhere. The limit as you get close to 2 is 6, but maybe the function value at 2 isn't 6. Can anybody come up with a counter example, or do you all think this must be true? Hmm? Am I saying anything in this statement about continuity? Am I saying that f must be continuous here? No. Okay. Can you come up with a function that has a discontinuity but is defined everywhere? Here's what I'm asking you. Can you build a function that has a discontinuity at x equals 2, but it's defined there? In other words, put a hole at x equals 2. Let me show you what I'm talking about, okay? All right. Let me put another page in here. Okay, so build a function. Okay, so that's what I want to do. And I want the limit as x approaches 2 of f of x to equal 6. Okay, can anybody think of a way to do this? Two. Okay, can anybody come up with a strategy? Can you describe it? All right, here's a function that essentially has the point 2, 6 equal, right? F of 2 equals 6. Okay, and it can look like this. Okay, so what's true about this function, f? What's true about this function is the limit as x approaches 2 from either side is 6, right? As I write up the function this way and I get close to 2, my limit's close to 6. Okay, as I come down the function this way towards 2, my limit equals 6. Okay, suppose instead of a circle there, though, I put a hole. Okay, well, now you're looking at it and you're saying the limit is still true, but now the domain isn't negative infinity to positive infinity, right? Because I've got a hole there. How can you fix this problem? Can anybody come up with a way to fix the problem that 2 is not in the domain? Guys, anybody have any ideas? What I'm saying here is the function output at 2 isn't defined. Can you define it as something other than 6? Try to make a function where 2 is in the numerator and denominator. Make it. Again, I'm not trying to come up with a function rule. I'm trying to come up with a picture. Don't make it complicated. I'm trying to come up with a graph. Okay. Can f of 2 be something other than 6? What do you think? Why not? How about f of 2 equals 1? We've seen graphs like this all the time. Okay, this is a piecewise graph. It's got a rational function when x is not 2, and it's got a particular value when x is 2. Okay, so maybe Raven, you were looking for a rule that would look like this. Okay, so this could be part of a rational function that has a hole at x equals 2. Okay, so here could be a definition. Okay, a potential definition. Okay, it's a rational function with a hole at 2. Okay, when x is not 2, and then when x is 2, it's 1. Okay, it's a piecewise function. I'm not asking you to come up with a rule, though. I'm just asking you to come up with a graph. And now the domain problem goes away because the function is now defined everywhere. Okay, so my domain, negative infinity to positive infinity. Okay. All right. So basically, the statement that we had in the practice problems is false. Okay, because I was able to come up with a counter example. Okay. Anybody have questions? Again, this part up here you didn't need to come up with. Okay, I'm just trying to show you what sort of function might give rise to a graph like this. Okay, maybe there's something special about the x value too. All right, and it doesn't fit the pattern that we've been using so far. Okay. Questions? Guys, what do you think? Right. Okay, let's take a look at what's left. Okay, so we said this one was false. Okay, I want to do this definition of the derivative. The only two I'm going to be able to do in the time we have left are 24 and 25. I won't have time for 26. 26 is not calculus. This is just an exponential model. Okay, this is also an exponential model that you solve with logs. Solve with logs. Okay, so those 26 and 27 are not calculus questions. So I'm going to skip them, but I will work them out in the notes that I upload. Okay, I do want to do definition of the derivative, okay, using the limit of the difference quotient, and then find the equation of the tangent line at the 0.15. Okay, I want to do these two. Okay, the graph of the derivative, remember the way I said to do that one is locate the turnaround points first. And there you're going to have a horizontal tangent. Okay, so basically at -3, your y value of your derivative is going to be 0 because it's tracking the slope of the tangent line. And the same thing at +2. Okay, here your slope is negative. So that means this graph will come from the negative side up like this. Okay, and in between this turnaround point and the other one, the slope is positive, so it's going to come up like this. And then your slope is negative on the right side of that second point. Okay, so this tracks the slope of a tangent line. Over here. Okay, so negative slope, positive slope, negative, negative. Okay, so y value of this graph is tracking the slope. All right, so this is just sketching a derivative. Please practice this, okay? Remember, I've put an app in the course that will sketch the derivative of a graph. All right, so play with that app until this makes sense to you. Okay, this will help with your understanding tremendously. Okay. All right, let's do 24 and 25. I'm going to use the derivative limit of a derivative difference quotient to find this derivative. Okay, so let me do that one next. So I'm going to work number 24. Okay, and here's the what I'm going to use for the limit as h approaches 0. F of x plus h minus f of x. Remember, these are two y values that are really, really close together. How far apart are they? Well, the difference in the x's is only h. Okay, and h can be super, super small. So we're going to let h approach 0. And then this is the slope of a secant line between the 2 points. But as I take the limit, okay, these points get so close together that I get the slope of a tangent line. Okay, so let me start with my function. Okay, I had f of x is x cubed plus 5x plus 4. Okay, that's what was given. Then I have f of x plus h. Okay, so everywhere I have an x, I'm going to put an x plus h. Okay, so I'm just substituting x plus h in there. Okay, now here, you might remember from what we did before, okay, there was a certain pattern to what came out of this. Okay, when we cubed a binomial the last time in one of the other problems, you can do x plus h times x plus h times x plus h. Okay, do the FOIL. But what you're going to get is you're going to get x cubed plus 3 x squared h plus 3x h squared plus h cubed. Okay, and what's happening is the exponents on x are going down, 3, 2, 1, 0, and the exponents on h are going up, 0, 1, 2, 3. Okay, the coefficients are 1, 3, 3, 1. Okay, again, I'm trying to speed things up because we're running out of time, but we did this once before. All right, so that's this part. Okay, the next thing I need to do is distribute that. Okay, so that's going to be plus 5x plus 5h. Okay, and then the last thing is add the 4. All right, everybody all right with that? So this is the whole expression. So f of x plus h is x cubed plus 3x squared h plus 3x h squared plus h cubed plus 5x plus 5h plus 4. That's the whole thing. All right? Now, if I put this into my difference quotient, here's what I get. The limit as h approaches 0 of this whole bit okay, there's the f of x plus h. Now I'm going to subtract the original function. Okay, so here's the f of x. And this is f of x plus h. Right? So again, I'm just subtracting the original function. And what you can see is the x cubes are going to cancel. The 5x is going to be positive here, negative here, and then positive 4, negative 4. Okay, so this is going to leave me with the limit as h approaches 0 of 3x squared h plus 3x h squared plus h cubed plus 5h, the whole thing over h. Okay, and what you want to notice about what's left is all of the terms have an h. So we can factor out an h. Okay, factoring an h out of everything in the numerator because there's an h in every term, and then cancel that out. Now there's no problem taking the limit as h approaches 0 . Okay, now if you just plug in h equals 0, this term's going to go away, and so is that one, because they have h's in them. And you're going to be left with 3x squared plus 5. Okay, this is f prime of x. It's your derivative function. Okay, so what this will do is you can plug in any x value you want. All right, and this function f prime will give you the slope of the tangent line to f at that x value. Okay, so if I wanted to know the slope of a tangent line at a particular value of x, I could just plug that value into this derivative function and boom, I would get the slope of the tangent line there. Okay? This isn't hard. This is tedious. Okay? It's tedious to actually expand out binomials or cube binomials. It's tedious to keep track of the signs of everything, but it's not hard. Okay? Everybody okay with this? And again, what I've gotten here is a derivative function. Okay, and this function will give me values of the slope of the tangent line to f. Okay. This is tedious. Yes, don't worry. Okay, we'll have faster ways to do it. We'll have faster ways. Okay. Now, unfortunately, it looks like I'm already over time. So let me go back to here. Okay. And again, the only problem I didn't get to was 25. So you're going to have to look at 25 in the notes. But I'll talk to you about the strategy. Find the derivative function. F prime of x, or y prime, because they're calling it y. Find the derivative y prime, plug in x equals 1. Okay, to get slope. Right? So you're trying to find the equation of the tangent line. What do you need to find the equation of a line? You need its slope. Okay, so here's how you find its slope. Find its derivative and plug in the value that you're interested in finding the slope for. That's x equals 1. Okay, then use y equals mx plus b and 1, 5 to get b. Okay, again, I will show you this in the notes. Okay, the only part that's calculus is finding the derivative. The rest of the problem is all algebra, and that's using a slope and finding a y-intercept in order to build the equation of a line. Okay, so this one, number 25, uses the same skills that we used in 24. Okay, so pretty much what I would say is review my notes and ask questions. Okay, you don't need to take this exam until Sunday. All right, so you have plenty of time to review. There's no new material this week. Okay, but I would say it's important to be able to do these problems on your own. Okay, so yeah, look at my notes, but see if you can do the problems on your own. Okay, I'm going to come back to the meeting and I'm going to ask people if you've got questions on anything. Again, most of what we've done since the start of the semester is a very little bit of calculus and a lot of algebra. Anybody questions?